Nothing is more powerful than a supermassive black hole, but according to a group of researchers, these massive objects at the centers of many galaxies might be driving the expansion of the universe. This bold claim comes from an international team that studied the growth rates of black holes in different galaxies. They suggest that the varying masses observed could be explained by black holes containing dark energy cores, the mysterious force behind the universe's accelerating expansion. If true, this idea would link two of the most puzzling concepts in physics, black holes and dark energy, and suggest that the source of dark energy has been right in front of theorists for decades. However, some leading theorists are very doubtful about this idea. The evolution of our understanding of the expanding universe. For about 100 years, since scientists first measured the distances to galaxies beyond our Milky Way in 1923, we've observed something significant. The farther a galaxy is from us, the faster it seems to be moving away. When we connect these observations to Einstein's general relativity, we realize that the universe is expanding. It's like a cosmic race between the initial explosion pushing everything apart and the gravitational pull of all the matter and energy trying to bring it back together. Think of the Big Bang as the starting point of this cosmic race. For many years, based on observations and analyses, scientific theories about the universe's fate have evolved. Scientists considered three main possibilities for how the universe might end. The Big Crunch, where the universe expands rapidly, then slows down, reverses direction, and collapses back in on itself due to the gravitational pull of all its matter and energy. The Big Freeze, where the universe expands indefinitely without ever stopping or reversing, with everything gradually moving farther apart. And the Goldilocks scenario, where the universe balances on a fine edge between expansion and contraction, where even a tiny change could lead to either a collapse or eternal expansion. However, when scientists analyzed the data in the 1990s, they found that the universe wasn't following any of these scenarios. Instead, the universe was expanding at an accelerating rate. Distant galaxies were moving away from each other faster than before. This unexpected acceleration led to the discovery of a new type of energy, unlike any known form of matter or radiation, which scientists named dark energy. The term was coined by American theoretical cosmologist Michael Turner in 1998. Dark energy. As scientists studied the expanding universe more closely, they discovered that dark energy behaves like a type of energy intrinsic to space itself, similar to what Einstein described as the cosmological constant in his theory of general relativity. This discovery was not just puzzling, but downright baffling from a quantum perspective. In quantum theory, our universe is seen as containing real particles within the fabric of space-time, interacting by exchanging virtual particles. These virtual particles are mathematical constructs representing interactions between real particles rather than existing in the same way as real particles. Using perturbation theory, scientists represent these interactions with Feynman diagrams, which illustrate all possible ways particles can interact. By summing these diagrams with increasing complexity, such as tree diagrams, one-loop diagrams, and two-loop diagrams, scientists aim to better approximate our physical reality. There are also diagrams representing fluctuations in the fields of empty space itself, rather than interactions between particles. Like real particles, these diagrams can be calculated with increasing complexity to approximate the zero-point energy, the inherent energy present in empty space. Dark energy is a perplexing phenomenon driving the universe's expansion at an accelerating pace. It is largely elusive because it does not interact with electromagnetic radiation, making it virtually invisible. Scientists estimate that dark energy constitutes approximately 68% of all matter in the universe. Of the remaining 32%, dark matter makes up 27%, leaving only 5% for visible matter, the matter we can observe and interact with. Presently, dark energy overwhelmingly dominates the universe, driving its continuous and accelerating expansion, but its nature remains a complete mystery. In 1915, Albert Einstein unveiled his revolutionary general theory of relativity, a groundbreaking departure from Newtonian gravity. This theory transformed our understanding of gravity by proposing that it is not merely a force between masses, but rather the curvature of space-time induced by the presence of matter and energy. This conceptual breakthrough marked a significant advancement in our grasp of the fundamental forces governing the universe. Challenges and theories surrounding dark energy. The prevailing cosmological belief once centered on a static and timeless universe. To align his equations with this view, Einstein introduced the cosmological constant, lambda, in 1917. However, as time has passed, the presence of a cosmological constant raises many questions. Why does it not equate to zero, and how did it acquire its specific value? When scientists tried to calculate the zero-point energy of space using quantum field theory, the result was nonsensically large, far beyond expectations. Some believed this indicated our inadequate grasp of accurate calculation methods, presuming it should ultimately nullify to zero. This led to further questions. What exactly causes dark energy, and why does it act like an inherent energy of space itself, unlike matter or radiation, which dilute over time? Despite many new ideas emerging, such as new fields or parameters in physics, there hasn't been any evidence supporting these hypotheses. The behavior of dark energy aligns perfectly with what we would expect from either a cosmological constant in general relativity or the zero-point energy of space in quantum field theory. However, from a theoretical standpoint, this poses significant challenges and complexities. In the mid-2000s, an intriguing idea about dark energy was explored. Some suggested that dark energy might be linked to the negative binding energy created during the formation of cosmic structures like stars, galaxies, and clusters. This binding energy results from the gravitational interactions within the universe's intricate cosmic web. Our equations for understanding the universe's expansion operate under the assumption of the cosmological principle, which posits uniformity and consistency in all directions. While this premise holds for large-scale structures such as the cosmic web spanning immense distances, it falters on smaller scales where the universe exhibits notable variations. One interesting analysis involved quantifying the effects of this inhomogeneity energy to see how it influences the universe. This analysis considered gravitational potential energy, inhomogeneity energy, and kinetic energy arising from gravitational imperfections throughout the universe's history. However, these factors never rise above a certain level of influence and don't behave like dark energy, which acts as a cosmological constant or an inherent energy of space itself. The only potential place where this effect could happen, known as a back reaction effect, would be within the singularities of black holes. However, this concept was challenging to calculate and seemed unlikely to be significant for several reasons. Connection between black holes and dark energy. Firstly, when scientists calculate the gravitational binding energy within black holes, it's only about 0.01% of the energy needed to explain dark energy. Secondly, for dark energy density to remain constant over time, the number and mass density of black holes would need to remain stable. However, these densities decrease over time, especially in the late stages of the universe. Lastly, while individual black holes do grow over time and new ones form continuously, this growth occurs much more slowly than the rate at which the universe expands. Although no comprehensive calculation had been done on how energy in black holes contributes to the universe's expansion, it didn't seem like a very convincing explanation. It was utterly surprising when headlines declared that black holes are the source of dark energy. Even more astonishing was that this assertion was not grounded in theoretical calculations, but rather on observational evidence, which was truly remarkable. The main idea is that black holes, particularly supermassive ones, are somehow connected to the expansion of the universe on its largest scales. The specific way they interact with the universe's expansion could potentially explain some of the effects we observe related to dark energy. The claim that black holes are the source of dark energy is indeed bold, and it's natural to approach it with skepticism. So let's examine what leads researchers to make such a claim. Researches and claims. Firstly, researchers consider what we know about black holes from various observations. Stellar mass black holes merge and emit gravitational waves, and we've observed photons bending around a black hole's event horizon. We've also seen hot plasma, gas, and stars orbiting supermassive black holes in galaxy centers, emitting light. Based on these observations, scientists have found that black holes in our universe typically rotate extremely rapidly, often close to the speed of light. This means their singularities aren't just point masses, but have angular momentum, giving them complex interior geometries, described by the Kerr solution in general relativity. The connection between black holes and dark energy is still a developing area of research. The idea is that the rapid rotation of black holes could somehow influence the expansion of the universe on large scales. However, the specifics of how this connection works and whether black holes indeed contribute significantly to dark energy are still subjects of ongoing investigation and debate within the scientific community. Therefore, while the idea is intriguing, it's essential to approach it cautiously until additional evidence and research either support or disprove it. Working with general relativity can be extremely challenging, especially when dealing with complex systems in the universe. One of the exact solutions found in general relativity is for a universe with a cosmological constant equivalent to dark energy, known as the de Sitter solution. Another exact solution describes a universe uniformly filled with matter, radiation, and other forms of energy. This solution, known as the Friedmann-Lemaitre-Robertson-Walker (FLRW) solution, describes the dynamics of an expanding or contracting universe. Interestingly, you can combine the solutions for a point mass and a cosmological constant to get a space-time known as Schwarzschild de Sitter. Similarly, combining the solutions for a rotating point mass and a cosmological constant gives you the Kerr de Sitter solution. However, our universe is more complex. We live in an expanding universe with a cosmological constant, matter, and radiation. Ideally, we'd like to combine the complete FLRW solution with the Kerr solution by embedding a rotating point mass within it. Unfortunately, we don't have an exact solution for this scenario. Some scientists have tried to connect the growth of realistic black holes to how the universe expands, even far from the black hole itself. They studied different types of galaxies from various times in the universe's history, including nearby ones, modern ones, and those from about 6.6 billion, 7.2 billion, and 9.6 billion years ago. They assumed there's a universal link between the mass of a galaxy's central black hole and the mass of its stars. This link might change over time but should stay consistent at any given time. They used a model called cosmological coupling to connect the black hole's mass at a certain time to when it starts influencing the universe's expansion rate. They looked at a parameter called k to see if it stays the same over time. If k is 0, there's no connection, and the black hole's mass stays the same over time without affecting the universe's expansion. If k is 3, the connection is strongest, and the black hole's mass grows as the cube of the redshift ratio, acting like it's adding to dark energy. If k is between 0 and 3, the black hole's mass grows, but not as fast. It still affects the universe's expansion, but not as much as dark energy. The researchers analyzed different galaxy samples to see if k stays the same across all of them. If it does, it supports their idea that black holes influence the universe's expansion. They found evidence suggesting that black holes are linked to the universe's expansion and act like dark energy, with k consistently being 3 across different galaxy samples. They argue against the idea that black holes aren't connected to the universe's expansion based on statistical evidence, but there's still doubt. However, it is highly unlikely, though not entirely impossible, that a connection between black holes and dark energy truly exists. The default assumption should be that black holes behave like any other mass in the universe. The empirical approach of measuring the masses of supermassive black holes and stars in elliptical galaxies to infer cosmological coupling overlooks a crucial question. How do these black holes actually grow and evolve over cosmic time? Without understanding this, we risk misattributing observed effects. Based on current data, dark energy behaves consistently as a constant throughout the universe, resembling the zero-point energy of empty space. If dark energy behaves differently, future observatories and experiments should reveal such deviations, which could significantly impact our understanding of the universe's fate. Despite its intrigue, the idea of a significant cosmological coupling between black holes and cosmic expansion is met with skepticism. It's essential to understand that dark energy is not a form of negative energy or repulsive gravity, but rather a type of energy that remains constant as the universe expands, unlike matter and radiation, whose densities decrease. This constancy causes galaxies to move away from us at increasing speeds. However, there's uncertainty if dark energy truly maintains a constant energy density.